Hello everyone, I am Satyajeet. Today I will present our work RNBF, real-time RGB-D-based neural barrier function for safe robot navigation. Let's get started. Ensuring safety during robot navigation in unknown and unstructured environment remains a key challenge, especially when robot location and geometries are not available beforehand, and the robot must rely entirely on the onboard sensing such as an RGB-D camera, which provides noisy and partial observation. At the same time, many safe reactive controllers based on CBF requires access to continuous and differentiable barrier function, typically represented as sign distance field. Reconciling these requirements is what makes this problem challenging. Many existing CBF-based navigation methods assume prior knowledge of obstacle location and geometries, or even a predefined map. More recent vision-based CBF approaches attempt to use RGB-D sensing but often require significant offline training or modify the standard CBF formulation to accommodate the perception input. As a result, the key assumptions behind the CBF such as continuity and the first order differentiability are often relaxed. In addition, the effect of depth noise from affordable RGB-D sensors on barrier construction is typically not explicitly considered. These limitations motivates the need for a framework that can construct valid barrier online directly from RGB-D sensing. Formally, we consider a robot operating in an unknown environment with access to RGB-D measurement and camera approach. Our objective is to process this noisy observation online to construct continuous and differentiable SDFs which can directly be used as a barrier function within the standard CBF-QP framework to ensure safe navigation. The contribution of this work are threefold. First, we generate SDFs in real time from raw RGB-D input using an online neural SDF representation. Second, we explicitly account for depth noise in affordable RGB-D sensor by adopting a noise-aware SDF learning objective. Third, leveraging the resulting SDF, we construct the barrier function in real time without prior training and integrate them directly with standard SDF-based reactive controllers such as CBF-QP. Now let's get into the method section. This figure shows the full RNBF pipeline. At high level, the system consists of two coupled modules. The top module constructs a SDF online from RGB-D input at 5 to 15 Hz. The bottom module is a reactive controller that runs at high frequency and uses the learned SDF to enforce safety. I will now walk through these components step by step. We start with the post RGB-D image and first apply a segmentation step to mask the floor so that it is not treated as an obstacle. We then use active sampling together with a small keyframe set to select 3D query points along the camera range. These points are used to train the neural network online that represents the SDF. The output of this SDF generation module is a continuous SDF and its gradients, which are updated in real time. The learned SDF is used directly inside a standard CBF-QP. Now at each control step, the neural SDF is queried at current camera position to obtain two quantities, SDF and its corresponding spatial gradient. These two quantities are exactly what is required to define a control barrier function. The SDF and gradient term directly appears in the CBF constraint, as seen in the equation, which is enforced by solving a quadratic program that minimally modifies the nominal control input. Importantly, the CBF formulation itself is unchanged. The only difference is that the barrier function is now constructed online from RGB-D sensing. As for the neural architecture, we use a MLP with positional encoding to map the 3D coordinates to the sign distance values. This representation allows us to model complex geometries while maintaining continuity and differentiability, which are required for downstream CVF-based control. To summarize the methods so far, RNBF constructs a continuous sign distance field online from RGB-D data, and this SDF is used directly inside a standard CBF QP to enforce safety. Next, let's discuss the loss function. The loss consists of three components: SDF, gradient, and the equivalent loss. The SDF loss supervises the sign distance values and is split into two components: free space loss and a near surface loss. The free space loss helps the model learn valid distance values away from the observed surface, while the near surface loss provides tighter supervision close to the geometry. The gradient loss supervises the direction of SDF gradient, while the equivalent loss ensures that the learned model satisfies the equivalent equation, enforcing a valid distance fit. Together, the SDF, gradient, and the equivalent loss enable stable and online learning of continuous and differentiable SDFs. Now let's discuss why depth noise matters in practice. Now, when deploying our pipeline on real robot, we use an Intel RealSense RGB-D camera. Now, this camera is affordable but produces notable noisy depth measurements. Now, prior works typically use a L1 loss for the near surface term, which works well when the depth measurements are relatively clean. Let's see what happens to the reconstruction when the depth has noise. Left, you see two scenes with a flat wall and a cluttered room. On the right, you see their respective SDF reconstruction using L1 near surface loss. Now we can clearly see these various artifacts and high frequency variation even in these simple scenes. Now these artifacts propagates into the SDF and its gradients, which are used directly by our reactive controller, making the resulting SDF unsuitable as an approximate barrier function. It turns out the solution is simple. To mitigate this issue, we adopt Hubel loss for near surface term. The key idea is to reduce the influence of large error caused by noisy depth outliers while still enforcing tight supervision close to the observed surfaces. Compared to L1, the Hubel loss prevents depth noise from being amplified, resulting in a smoother SDF geometry and more stable gradients. The choice of delta significantly influences the reconstruction quality. Smaller values of delta suppresses the noise, but risk over-smoothing the fine details, while larger value of data retain geometric features but may allow noise to propagate. In our real-world experiments, we found delta ranging from 0.01 to 0.05 offer a favorable balance, though it remains a tunable parameter depending on the quality of depth sensor. Although we do not claim perfect fidelity, the result is sufficiently accurate for our pipeline. Now we move to the robot experiments. I will start with the simulation result. We simulate a realistic hospital environment using gazebo as shown in the figure. 4 scenarios are defined based on different initial and target location, each representing distinct navigation challenge. The video shows comparison of parametric CVF QP with RNBF CVF QP in scenario 1. So parametric version assumes full knowledge of obstacle location and geometry using ground truth SDF, while the RNBF builds the SDF online. As we saw in previous video, the RNBF version and the parametric version achieved the goal collision free. However, the RNBF version requires slightly more time to reach the goal owing to its exclusive reliance on online RGB-D sensing to construct the barrier function, compared to the parametric version which uses full prior knowledge of obstacle location. We finally tested the RNBF in rest of the 3 scenarios. The result is similar to scenario 1, and RNBF CVF QP safely navigates in these unknown environments. For real-world validation, the Fetch robot is equipped with an Intel RealSense RGB-D camera, for perception and a motion capture system for real-time pose estimation. The real-world experiments include both static and quasi-static obstacles. For the first experiment, we use a single obstacle and compare nominal control to RNBF CBF QP. As expected, the nominal controller collides and RNBF CBF QP safely navigates around the obstacle and reaches the goal. Next, we redo the experiment with a single obstacle of a different shape. And as you can see, the results are similar to the previous one. And the RNBF achieves the goal. Next, we increase the number of obstacles as seen in the video. Now, as you can see, we achieve similar success rate. Finally, we further amplified the difficulty of the task with quasi-static obstacle. Initially, the human is out of the sight of the robot. Once the robot starts moving, human comes in the trajectory of the robot. Now, as you saw, the robot safely navigates around this challenging scenario. To conclude, RNBF enables continuous and differentiable SDFs to be constructed online from noisy RGB-D depth data. We find that explicitly accounting for depth noise is necessary for reliable real-world safe navigation. We demonstrate the RNBF using CBF QP controller. However, the RNBF safety filter can be readily adapted to other SDF-based reactive controllers that consume SDF and gradient information. Thank you for your attention. Feel free to scan the QR code which will take you to the project website. There you can find the paper, link to the code and other experiment videos. Thank you very much.